Um, Hello, everyone. Just a quick update. The paper is now accepted and online. It's stuff that most of us already know, but just in case there are uh, complete newbies among us. So we know that passive acoustic monitoring, it's been like a common method for birds and bats for some years now, especially bats. The idea is that we can leave the recorders in the field and come and collect them later and see what's been singing or echolocating there. In the past, this method was quite expensive. Like recorders could cost several hundred or even €1,000 per unit. They would only last for a few days, and you would generate a huge amount of data and have to go through it one file at a time. But now the recorders are getting cheaper, and machine learning classifiers mean that machines can do some of that work for us. You'll notice I said some and not all. We don't want to be an AI tech bro or whatever the term is nowadays. Right. After the bat classifiers, some new classifiers were developed, such as Bennett. But the really exciting thing for us is that there are now systems that let us train our own classifiers for the groups we're interested in, specifically grasshoppers and other insects. So to get a bit more specific, I'm mostly working with the AudioMorph system. These systems are very inexpensive, so around €80 per unit if you're willing to wait 4 months for delivery. They use standard micro SD cards, standard AA batteries, and depending on how you program them, there's a user interface, don't worry. They're very flexible. So you can record up to 192 kilohertz, which is more than enough for any known insect. And if you give them decent batteries, they can last weeks. You can tell them to record during the day, at night, even synchronizing them to sunrise and sunset with their latest user interface update. In my study in Schleswig-Holstein, northern Germany, way up near the Danish border, I compared them with bat loggers, which cost €1,000 per system. And during the 3 days the bat logger batteries lasted, AudioMorphs performed equally well. Except my AudioMorphs lasted for 2 weeks, not 3 days. And during that extra time, AudioMorphs detected extra species. I also compared them with traditional transect netting, so going out with a net and the Mark I human ear and looking for insects. And they performed roughly as well, with some trade-offs. So AudioMorph passive acoustic monitoring detected nocturnal species better because they were there at night. We only netted during the day. The downside was that netting detected Mammaliotetrix maculatus, while AudioMorphs did not. This was a common sense failure on our part because when we had the AudioMorphs out, Mammaliotetrix maculatus had already stopped singing for the year. I suspect if we had just deployed them earlier, we would have detected them. And in fact, last year, I did detect Mammaliotetrix maculatus with AudioMorphs when I went looking for them at the correct time.
David, are you able to set the presentation in presentation mode? Because maybe the screen is
Cool.
a bit small out. Yes, that's great.
My fault. Sorry, everyone. Okay, now speaking of presentation mode, as Baldwin said, I'm hoping you guys will be able to hear this recording. Did you hear that?
I didn't.
Fortunately, we have a backup. Basically, this recording is from one of my standard field sites in 2022, and it contains several species, 3 species. Pholodoptera griseoptera, I'm sure we're all familiar with that. And it also has Cortipus dorsatus, which was not previously known from this location. But when we went to net it after these recordings, we found it and we were very excited. Okay, so I will now try to play this from my phone. No, don't send me notifications, you awful app. Shush. Oh, for goodness sake. Okay, I was hoping to actually play the song for you, but my phone has.
Okay, it's not working. We can move on.
Okay. Suffice it to say, it's there, and if PowerPoint would play the audio to you guys, it would sound very cool. Um, um, but during my research with audiomorphs, I've discovered some things. For example, the distance from the device to your singing individuals can greatly influence how they look on the spectrogram. So, for example, these 2 recordings are from the same site at the same time, but the 2 devices were about 50 meters apart. And you can probably clearly see at around 20 kilohertz, we've got Rosaliana rosalie, while much higher in the ultrasonic range, we've got Conocephalus dorsalis. And you can see that this upper recording was at the very edge of the range where Conocephalus dorsalis, you can clearly tell what it was. Whereas down here, for the first time ever, Rosaliana rosalie is a lot less prominent, and it's a lot easier to tell what Conocephalus dorsalis is. As I'm sure most of us know, song frequency can also vary based on factors like temperature. For subsequent classifier building, I've tried to incorporate this by using as broad a selection of recordings as possible. So not just spamming 200 recordings from the same individual, same device, same day. I've deliberately tried to take as many locations, as many singing individuals, as many distances, as many temperatures as possible, to hopefully try to make the classifier a bit saner. I will say, hint, 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 that if anyone has more data to share, I would greedily accept it to improve my classifier further. Like I said before, when recording, we need to get the timing right. The species don't sing 24 hours a day, 12 months a year. Even if your species is there, if you put the recordings out too late or too early, you won't hear them. Some species can only be heard when your devices are relatively close. Others you can hear from a much greater distance. In North Germany, for example, Tetragonia viridissima, you can hear it from a considerable distance. Staphylophila grossum, you have to be right on top of the stupid thing. I should also mention, when you're looking at my species list in a minute, that species list might not be perfect if you run it in Southern Europe. So when I say it's Rosaliana rosali, you can't tell if it's Rosaliana rosali or Rosaliana azama. Like, they look indistinguishable on spectrograms, and if there's a way to tell them apart, I haven't figured it out yet. I suspect that will also be true for Pholodoptera griseoaptera and Pholodoptera aptera, and I've got my suspicions for other species as well. I'm sure Bodwin probably knows better than I do, so I will be sending him many emails to ask for help this year. I apologize in advance. I should also mention that some species, they make sound, they make species-specific sounds, but they might not be practical. For example, Sphinganotus chiralens and Oedipoda chiralescens, I have made dedicated visits to sites where they are abundant. There are hundreds of them. It's a perfectly sunny day, perfectly hot. I go there, I see them, they have blue wings. I see them that they're in the middle of courtship and they make no noise. Or they make really quiet, really infrequent noises. So for passive acoustic monitoring, how practical are they? Don't really know yet. That's something I have to bash my forehead against. Especially for you guys in southern Spain, where I know you have a lot of Sphinganotus. That's something you might want to keep in mind. Even for the species in my classifier, especially Staphylophila grossum, this can still be a problem. So when my classifier detects it, you can be reasonably confident it's actually there, although my classifier still sometimes gets vegetation noise mixed up. Frankly, even I have trouble with that one sometimes. But really, I would suggest you go there with a net to confirm it's there when it's a borderline species. For others, like Cortipus bigutulus, Tetragonia viridissima, Stenobophorus lineatus, you hear it, you know it's there. Happy times. Okay. So for actually building up the classifier, we used the Open Soundscape package in Python. This lets us build our own classifiers and run them in Python. It's not necessarily as user-friendly as a pre-built system like Batscope, but it lets us build it up rather than relying on someone else's species list. It's also free, so we don't have to pay for every gigabyte we're running, unlike some paid services like the BTO acoustic pipeline. To begin, I used the Xenocanto database, the Orthoptera species file, Tierstimmen Archive Berlin, Bioacoustica, and private contributions from, amongst others, Klaus Rieder and Ian Middleton. We then augmented that database enormously with data from 41 sites in Schleswig-Holstein, made with AudioMoths and BatLogger. This worked well at first, then we strengthened it even more with visits to 6 sites where we knew exactly what was singing. This let us cheat a little bit by putting 6, 10 AudioMoths at various distances, angles, and times where the species was singing to create a huge amount of training data relatively quickly. So the downside of this approach is that for some species on databases, we have a lot more training data than for others. So for example, Gryllus campestris, you can see we've got a huge amount of training data on the databases. And I've subsequently gathered an enormous amount of data in the field. For other species, for example, Calyptimus italicus, which I'm hoping to add this year. I hope if I spelled it correctly. Okay, for Calyptimus italicus, we only have 3 recordings on Xenocanto. But yeah, you understand what I mean. In the initial version, we have 17 species, all of which were verified by local Orthoptera experts. And the initial version had a true positive value over 80% and a false and negative value below 10%. So generally, if it says the species is not there, you can assume there are no recordings where it was singing and the system just missed it. The downside is that the true positive value of 80% is good, but it can still be too optimistic sometimes. It especially sometimes thinks Stephophyma grossum is there when it is in fact not there. I'm working on improving this. So for example, the original version finished development in 2024, in March 2024. And I then spent the whole summer gathering more recordings to improve it. This includes time spent with you guys in TEOSS in Italy, from Prague, Bavaria, Schleswig-Holstein, and from friends elsewhere in Germany. So to actually build up the classifier, what we do is we take our recordings, be they from Xenocanto or recordings we made ourselves in AudioMoth, and we load them up in Raven Light software. It's free and very easy to use. So we deactivate waveform and we zoom in. Now, this recording here has both Poecilimon ornatus and Gryllus campestris. If we zoom in, you can just about see it here. if I were to be able to play the sound to you, you would hear it quite clearly. We then isolate the sounds we want and create a tag. That seems easy. Doing it the dozens or hundreds or ideally thousands of times gives us a database. What we do, imagine I did it for every single sound on this WAV file. We save this as a selection file, which is basically a text file telling the software, okay, during these parts of the sounds, these frequencies, this Orthoptera is singing. Otherwise, it's not singing. Where's it gone? What we end up with is folders full of WAV files and corresponding text files. So each WAV file has a text file. We can then load that into Python with a list of labels, and you have to make sure you get the spelling exactly right every time, or as a hissy fit, to train something called a convolutional neural network. It then breaks every WAV file up into clips, checks your text files, and for each label goes present, 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 absent, absent, absent. And for each clip, the machine looks at the spectrogram, looks at the shape of the sounds in that clip, and builds up machine learning voodoo so it learns what the sounds look like. That's why it's important to have so many samples of each one. And what you eventually end up with, after a lot of stress and leaving your laptop on for 2 days processing it, is this, a CNN model. We can then use the code to run that model. Is it gone? Here we go. On a folder full of WAV files. For example, this one of 10,700 files. If you can imagine checking that one file at a time, we get an Excel file, which will hopefully load, thank you, on a reasonable timescale. So for each WAV file, we get a list of confidence values for every species we've trained the classifier for. We can go, for example, Rosaliana Rosalie. Ugh. Sorry about this, it's a €2,000 laptop. I don't know why it's so slow. Let's start with the highest confidence WAV file. And if we open it up, we will see unless it's wrong, in which case I will be incredibly embarrassed. Which one was it? Two o'clock and 6 minutes. That's because I'm off by 2 days. That's embarrassing. Two o'clock and 6 minutes. There we go. Rosaliana Rosalie. A flagrantly obvious example. Like if you've ever come across Rosaliana on a WAV file, you will be able to tell. And I will say in Schleswig-Holstein, this one is everywhere. The good news is where you have huge folders full of data and you've got less common species, it means you don't have to check every file in a 10,000 file folder. It means you can just look for the species, and when it is there, you can say, okay, it's there. I can stop looking for that species. Okay. In addition to the original 17 species that you just saw in my original classifier, I'm prioritizing these species to add next. They're all in various stages of development. I'm prioritizing Gryllus campestris, Gryllotalpa, Omocestus viridulus, and Chrysacroan dispar, because those are high priority species for collaborators who want to use the classifier. But I plan to get to all 20 of them as soon as I can. And we've got lots and lots of data to actually do it. The main obstacle is finding time and coffee to go through and label what needs labeling. There's also a plan to add frogs into the classifier and pollinators. Ideally, I'd like to find a way to automate that to reduce labeling time. But that's for a related project. I just thought it was cool and something that could be mentioned. None of the work would have been possible without the help and advice of, amongst others, Bodwin, Klaus Rieder, and people who've shared data with us, such as Mark Schenziel-Orts and Lisa Price. I'm also indebted to the Bundesamt für Naturschutz and Deutsche Gesellschaft für Orthopterologie for helping to fund the research.